So no red on the board. Use blue. All right. Sorry. So let's remember, because we're always talking about this atom, right? Molecule. Okay. Right. So atoms to molecules, molecules to compounds, right? Compounds can then allow us to create this cell. Right? And so we got to go back to these atoms. We got to talk about those atoms. And we talked about the difference between atomic number, right? Atomic number versus atomic mass. Some periodic tables will have the atomic number up top and the atomic mass down bottom. Some will have them reversed. Just note the smaller number is always the number that's the atomic number. Yes?
On your test, do you want the atomic mass on the bottom?
No, I don't care either way. Yeah, I mean, I'm more concerned with whether or not you know that the atomic number for atoms. I'm more concerned, good morning, that you know that the atomic number is actually equal to the number of electrons, which is actually equal to the number of protons. That's what I'm concerned with. That's where it starts. Then for atomic mass, that the number of protons plus the number of neutrons, right? That's how you get the atomic mass. In the case of carbon, luckily enough, because carbon has, carbon can be, carbon 12, 13, or 14, carbon is isotopic. These are considered to be isotopes of carbon. The definition of isotopes would mean then what? Is it the number of neutrons or protons that are different? Neutrons. Everyone agree? So that's what makes isotopes. That's what makes isotopes isotopes. It's the variation in the number of neutral particles. Anybody know how we got that? Does everybody understand how we got that? Because look, if 6 is the atomic number and 6 is the number of electrons, which is equal to the number of positive charges, right? Number of negative charges equal to the number of positive charges. Then if my atomic mass is 12 and my number of neutrons is 12, then here I have what? 6 neutral charges, right? Because I have 6 protons. So 12 minus 6 would give me 6 neutral particles, right? N with the little 0 is my shorthand for neutron. Okay? Neutral particles. 6 neutral particles. But when we do the same thing for this guy, what do we get? 7 neutral particles. Everybody see that?
Yeah.
And then when we do it for that one? 8. Everybody see that? So sure enough, you know what's happening? So everybody's always worried about these GMOs and all that bullshit. Right? Let's be honest. Guys, you're eating this regularly. You're eating radioactive carbon regularly. And you're worried about GMOs? Seriously? You're worried about GMOs? I'd be more worried about this, wouldn't you? Because this is radioactive, isn't it? And you can't stop it. We can't stop it. It's in every one of us. And it's been a part of us ever since we've been a part of this earth. This is what gives rise to the fossil record. This is how we're able to date. Radiometric dating. This is what tells us how old a bone is. Because we know the half-life. We've calculated the half-life. So when we're alive, we can, based on size, we can only eat so much. Everyone agree? Some people bigger than others can eat more than others, yeah? But based on size, you can only eat so much. So when you die, that's it. You don't eat anymore, yeah? At that point, whatever you've eaten, a part of it has carbon 12, carbon 13, carbon 14. And the carbon 14 will disappear into carbon 13, and carbon 13 will disappear into carbon 12 over time. But there'll always be a little bit left. So when we find those fossil records in the caves, in this new cave of wonders, that has now found a new set, we found thousands. They found thousands in this cave. It was a burial place where they were taking the bodies and dumping them, and it's amazing. It's It's a new species of human. It's believed to be a new species of human that came out of Africa, which just proves beyond a shadow of a doubt that we all came out of Africa. Right? It's just years and years and years. So when they find those, they only got a small little bit of carbon-14, but it doesn't matter because once we measure that small little amount, we can go backwards. Because we know the half-life, we can figure out how old they really are. You see? Especially if we have full-size skeletons. You guys are interested, look it up, man. National Geographic last year. March of last year. Right? I'm sorry, guys. I'm a nerd. Read science magazines all the time. Most of what I read is science. Isotope, radiometric dating. Radiometric dating. Now, that's for those of you who are interested in forensics or forensic science. Right? What about clinicians? You want to know how an MRI works? Chemistry. We'll talk about this now. So now, that's the basis for understanding every atom on the periodic table. The atoms that you should know: hydrogen, carbon, oxygen. All right? So CHO and N, carbon, hydrogen, oxygen, and nitrogen. CHON. Very important that you understand those. Very important. All right? Because everything is based around that. If I want to make amino acids, I got to have carbon, oxygen, hydrogen, nitrogen. If I want to make fatty acids, I got to have carbon, hydrogen, oxygen. If I want to make glucose, I got to have carbon, hydrogen, oxygen. If I want to make DNA, I got to have carbon, oxygen, hydrogen, and nitrogen. Everybody see that? That's the basis of it all. There's the molecules, there's the compounds that make the cell. Oh. You understand? Of course, it's not that easy because I can't make a cell, can I? So can we argue that God is not really alive? I don't know. Could we? I mean, we could. If this was a philosophy class, maybe we could really argue that point. If God is truly alive, or if this is really just, a sick, cruel joke that we're all just evolving on this rock that's floating in space and we have no meaning in life at all. I don't know. But that's for another class altogether, right? But so, from this aspect, this is what makes us up, guys. This is what makes us all up. You think we're different than plants? I got news for you. No different. Plants need the same four carbon. They need the carbon, they need the hydrogen, they need the oxygen, they need the nitrogen. You understand? Anybody know how plants get nitrogen?
Soil.
From soil.
Yeah, from people.
From people, from human waste. But directly from bacteria that fixate the nitrogen and feed it to them. Talk about a symbiotic relationship, huh? And very interesting, isn't it? And wait, Professor P, I thought you was an anatomist, physiologist. No, I'm an ecologist too. I understand it. I gotta understand. Hey, if I want to understand the human condition, don't I have to understand it in the environment that I'm in? Yes? Makes sense? Yes. So it all comes back to this. It all goes back to chemistry. It always will come back to chemistry. That's the beauty of this, guys. You take me for this semester, next semester, and I have my 2086 students sitting here in class. Sure enough, I have one of the students who hadn't taken me for 2085 said, so did you suggest, they're in 2086, they're doing endocrine. Would you suggest that we go back and read chapter 3 about this thing because it says it about this in endocrine? I said, yeah, that's absolutely. Sure enough, everything that you will learn in 2086, guys, will always come back to chapter 2 and chapter 3. Every single bit of it. You want to talk about electrical physiology of a neuron or a muscle? You got to know about the electric. You got to know about, first you got to know about atoms. Because the main atoms involved there are going to be sodium as a cation and potassium. Potassium, sodium is the common extracellular cation. Most common extracellular cation. Potassium is the most common intracellular cation. Chloride is the most common extracellular anion. Phosphate is the most common intracellular anion. You understand that? Separately, another one that's common. They call that bicarbonate ion. Should not be called bicarbonate ion. It's called the hydrogen carbonate ion. There's nothing bi about it. Right? It's got one hydrogen on it. Why they calling it bi? They called that bi long ago. They were wrong. Wrong. You're gonna see they're gonna change it. So Rolaids, Tums, all these, by the way, guys, I just buried my cousin on Friday, right? He died of esophagitis. So any of you suffer from acid reflux, yeah? Y'all get that checked out. Y'all better get that checked out. Eat yourself some papaya, change your eating habits. You get stressed out and anxiety.
What if it's anxiety induced? That's what I was gonna ask.
What's that?
What if it's anxiety induced?
It can be anxiety induced. Man, let's deal with that anxiety. You gotta learn the triggers. Learn what triggers the anxiety and then avoid it. Or learn how to deal with it by constantly exposing yourself to that anxiety little by little, a little bit more, so you build tolerance to it.
So here's a follow-up. What if it is a chemical imbalance?
It's a chemical imbalance, then we treat it with medicines and behavioral therapy. Both. It's not easy. It can be done. But the person has to be willing to approach it head on and want to get over it and deal with it. So they don't have to, because it runs, man, you run the risk. Oh, I just, 63 years old, he still had a good 20 years of life left. So Friday I buried my cousin, and then Saturday I got this massive tension headache, and then Sunday I'm sitting up, laid up with kidney stone. So that was my eventful weekend, guys. All right, and yet I'm still here, still standing in front of you, giving a lecture. Sodium chloride, hydrogen carbonate ion. Everybody got me? Hydrogen carbonate ion. I will never write the name bicarbonate. I will always write it as HCO3 negative. Okay? I'm sorry? I will always write it. Yeah, I will always write it like that for the reason that you have to remember that this is the body's main extracellular buffer. And a buffer, by definition, is a chemical compound that resists changes in pH. So if I tell you, hey, we got a high hydrogen ion concentration in the stomach, how do I combat it? This guy right here. I have a high hydrogen ion concentration in the duodenum. How do I combat it? This right here. Acid-base physiology. The kidney's main role is to balance acids and bases in blood. How will it combat it? In the blood is very, 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 it's very precise with its pH. Anybody know what the blood pH is? Anybody know what blood pH is? 7.35 to 7.45. That's the range. Not a very generous range, yes? So 7.4, just above the pH scale, the regular 7.0 pH scale. Right? Remember, 7.0 is perfect. That's water. When water dissociates, it's at a perfect 7.0 because when a water molecule separates hydroxide from hydrogen, it dissociates both the same amount. And when it does that, it gives you this perfect pH balance, 7.0. Guys, all life is based on this. Why do you think we're on Mars looking for water? Because if we find water, we find
Life.
Life, or the possibility of life. You got me? That's how important water is. That's why you do an experiment with water to see how different it reacts to stuff like H2S, which is similar in structure but isn't the same. Something special about water. Something very special about water. 1, it has a perfect pH. 2, it has a bench structure, and its ability to pass through the membrane is key to life itself. You understand, guys? So water will always move in and out of the membrane because it's small and for the most part non-polar, even though the bonds are polar covalent in nature. So each one of these bonds are polar covalent in nature. Now we go back. You guys remember what we talked about? 0 to 0.7, 0.7 to 1.7, anything greater than 1.7, right? We talked about the story of, sharing the electron evenly versus sharing it unevenly versus transferring it, right? And that you had non-polar covalent bonds, polar covalent bonds, and then ionic bonds. And ionic bonds, guys, are between salts. Do you understand me? And salts are great when you're up here on the bench. Everyone agree? Go home. Look at the salt container. Put some in a cup. You'll see it's got structure to it, yeah? But the moment you take a little bit of it and put it in water, what happens? Dissipates. Why? Because there's the nature of every 1A metal and every 2A metal is to give up 1 or 2 electrons when they are in solution. They become electrolytes. That's what we are. We are 60% water, but that water is not water alone. It's water with accumulated salts, guys. Do you understand? It's not to say that there isn't potassium outside the cell. There is, but it's smaller than outside the cell. Does everyone understand that? And we're going to play a game with that. You'll see. Sure enough, when I want to play that game, I got to have a door open up. Come on in. Sodium, come on in, sodium. Or, come on out, potassium, come on out. Everybody see? That's muscle, that's nerve. And we're not there yet. But that's why I teach you stuff now. Calcium, very important. Look, I'll put calcium right here. And I'll put a big old star next to that because calcium, let me turn over this way. So make sure we get that side there. So calcium, I'll put next to star to that because calcium has 5 very important roles. 1 is to coagulate blood. 2, hey, if I'm a cell, everybody take a look now, I brought the model with me, the cell model. If I'm a cell and I want to throw anything out, I don't care what it is, protein, for the outside of the cell, hormones, whatever, I don't care what it is. Exocytosis, calcium dependent event. So that's why you need calcium. Okay, guys? All this is in your textbook. If you look up these ions, so I think on the first or second page, there's a table. And that table has each ion listed and the physiological effects that it plays in the human body. I would tell you to go and look at them. Okay? Calcium is the most important one. It's key. It's key. It's key. For exocytosis, coagulation of blood, formation of bone and teeth. It's required for any muscle in the human body to contract, and separately, the heart requires it for its electrical activity. Okay? We're going to deal with the muscle stuff. You're going to see it. That's what we're covering this semester. We're going to be covering the role that calcium plays in the formation of bone and teeth, the role that calcium plays in muscle contraction and the electrical aspect of cardiac muscle I'll mention, but you'll get into that next semester in 2086. And then, of course, calcium's role as it plays in exocytosis for neurons to release neurotransmitters so that we can respond to our environment, guys. You understand? This is why you want to know these ions. Are there any questions? Any other ions that are important, guys? What do you think? Can we put a whole list together? What other ones are there? Separate of the calcium, sodium, potassium, chloride, phosphate. What would I need phosphates for, by the way? Anybody? What's inside the cell? Energy. What's energy? Who makes energy? What organelle in the cell makes energy? Mitochondria. What is that energy that the cell is making? ATP. What is the name of ATP, guys? Adenine, phosphate. 3 of these. 1, 2, 3. That's what ATP is, guys. So would it make sense that I have these phosphates inside the cell? Yeah. Sure enough, they're so important for the inside of the cell that bone actually is made up of calcium and phosphate together. How you like that? Because I don't want to raid around and having to consume the phosphates that I need for inside the cell, yeah? I want to have a storage site for them. So sure enough, my bones are made up of calcium and phosphate because that's how important calcium is, and that's how important phosphate is to the cell. that make sense? It does. And all this is being fed to cells by blood. Everybody understand me? Through blood vessels. So it's the job of the blood and the blood vessels, not the red blood cell. What's the difference between blood vessel, red blood cell? Anyone? Speak up. Okay, so no, the red blood cells is for every cell in the human body. Its job is to carry oxygen. It's a cell with no organelles. It has hemoglobin in it, and its main job is to bind oxygen and deliver it to every single tissue that needs it. Right? Every tissue in the body. So it's very specialized. It's nothing like the cell. It is the one cell that I can tell you, hey, if there's a cell that you're going to choose from, and I ask you, a cell that is enucleated, blah, 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 blah. The moment you see enucleated, you're going to choose red blood cell as your answer. Does everybody understand that?
Yes.
Because there's no perfect example, no better example than red blood cells for a cell that will get rid of everything, including its mitochondria. No mitochondria, no nucleus, no ER, none of it. When it leaves the bone marrow and becomes a mature red blood cell, it is nothing more than a cell filled with hemoglobin inside that transports oxygen and carbon dioxide. So, that's another one. Let's write that up there. Anybody know what that is? That's diatomic oxygen. That's the gas that we breathe. That's the gas that we bind at the level of hemoglobin in the red blood cells, guys, in the lung. Okay? So you guys getting a feel for why I really didn't spend a lot of time in the chapter 1 where they talked about the different systems, because you're hearing me talking about them now. Right? When we're talking about all these things and how they're kind of interrelated. So that oxygen, that's diatomic oxygen. That's the way we breathe it in. Well, I'm here to tell you that the mitochondria